Welcome to the second class in quantum mechanics. Previously we were studying the uncertainty principle and the double slit experiment in the case of electrons, photons and bullets. Right now we would like to revisit those concepts. The first one is the uncertainty principle. Now suppose I want to have a proof of uncertainty principle from other point of view, which is a picture which you can see from the visor, and it also included here. Here we have a Fourier transform of 4 different figures. The first one being a pulse, which is written as fx. The pulse can be Fourier transformed to give you a wide function. The second one is wave packet, which we had encountered with recently. The third one is again a progressive wave, and the fourth one is basically a Gaussian function. For all those which we can see, we can always say that the product of the standard deviation, for if one is plotted along x as is plotted given here, the product of the standard deviation in the x space delta x and the corresponding product of the standard deviation in the k space, if I call them as delta k, must be always greater than or equal to half, which can be very easily seen or observed from the picture here. Because in the first case, although delta x is confined to a very small region, delta k is very large, so it would be all obviously greater than half. Why greater than half? It should be greater and it would be a large value. In the second case also it would be a large value. The limiting case is the Gaussian one, which can be mathematically proved by using a relation of the Gaussian function, and that has been proved in the previous semester also, that the minimum value is half. Now how do we really encounter this, or how do we really picturize this in terms of the principle which we recently learned, the principle or the hypothesis which is known as the de Broglie hypothesis. Now according to de Broglie hypothesis, the momentum p is given by h by lambda, where p is the momentum associated with the moving particle, or one can say lambda to be equal to h by p. And so we can say k, which is equal to twice pi by lambda, can be written as equal to twice pi by h into p. So if I now want to find delta k for this particular case, then this would be equal to, so this is p by h cross, and this can be written as delta p by h cross. So if you just substitute the value of delta k from here, then this can be written as delta x into delta p by h cross to be greater than or equal to half, which is something like delta x into delta p to be greater than or equal to h cross by 2. This is nothing but again the uncertainty principle. So one can arrive at the uncertainty principle from the Fourier transformed figure and from the limiting value of the Gaussian function in the x space and the k space. Now let us try to revisit the double slit experiment. What was the double slit experiment all about? Now we have, in the case of double slit, which we were talking about in the case of electrons, we had a pair of slit A and B. We have a slit over here and another slit over here, and there was an electron gun which was actually firing electron, and we had a screen over here from where we were observing the individual electron numbers by initially by closing one of the slit and then by closing the other slit. Now let us try to talk about quantitatively the exact configuration of the electron, not the configuration but the wave function of the electron in terms of suppose what is, if I ask a question in the case of double slit experiment, what is the chance that an electron in a double slit will pass through one of the slit? Now this is from the particle point of view. If I talk about the wave point of view, then we can always write the corresponding wave function due to the electrons emitted from the slit A, psi A, to be equal to some constant A e to the power I of k, and if I call this distance to be equal to, let's say, at any point y from this particular central position, if I call that as L of AY, then I can always write this as k of L of AY minus of omega t to be the wave function due to the electron wave reaching at the point y. In the same fashion, we can again define another wave function psi b to be, if it is of the same amplitude as a e to the power I of k of L, if I call this distance as L of by, then L of by minus omega t. Now what is the resultant wave function at this point? If we think the electron to be a wave according to the de Broglie concept, then we need to substitute this k by p by h cross as we had done recently, and omega to be equal to E by h cross by Planck's law. So this is something which was already defined as Planck's law, and this was defined as the de Broglie hypothesis. Okay, so let us try to rewrite psi a as equal to a e to the power I of p L-A-Y minus E T whole by h cross. In the same fashion, we can write psi b to be equal to a e to the power I p of L by minus E T by h cross. Now what would be the resultant superposition resultant of the two waves which are meeting at the point at a distance y from the central point? It would be a simple superposition of these two waves, psi a plus psi b, which can be written as a e to the power minus of I E T by h cross whole into a e to the power I of p L A y by h cross, and then e to the power I of p L B y by h cross. And if one can take common a e to the power I of p L of a y plus L of b y by 2 h cross common from this then, and multiplied by a to the power minus of I E T by h cross, then what we are left with is something like e to the power I P L of by minus L of ay by twice h cross plus e to the power minus of I p into L of by minus L of ay by twice h cross. Okay, So you can see that this is nothing but a cosine function. We can always replace this by a cosine function. We can write 2 of a e to the power I p. If I call this as L average by h cross, okay, and ip, okay, minus et a I p et by h cross, and this as cosine of p by twice h cross delta L. I intentionally call where I have introduced L average to be equal to LAY plus LBY by 2, okay, and delta L as L of by minus L of ay, which is actually the difference between the distance of the point of observation from the two sources A and B, that is delta L. And if I say that the slit separation is D and the angle between these two with the x-axis be theta, then this is also theta, and then we can use the concept of interference where we have written delta L to be equal to, if this is delta L, this length is delta L, then delta L is equal to d of sine theta. So one can very easily write the resultant intensity to be equal to I of PL average minus ET by h cross cos of PD sine theta by twice h cross. So this is the resultant intensity if you take into account of the fact that there is a wave associated with the electrons, and that wave is the de Broglie wave. The corresponding wave functions are given by this particular form. Then the resultant wave would have the amplitude or the displacement to be of this form. And obviously, if one talks about the intensity I, if I talk about the intensity of the resultant wave, which would be obviously proportional to chi square, mod of chi square, because chi in itself is a complex number, then this should be obviously proportional, because there is a factor e to the power I, it would cancel out and it would be proportional to cos square of PD sine theta by twice h cross. So basically the picture which I drew in my last class, which was a function, it was basically a function of the type like this, which was a cos square function, and which this cos square function would have alternate high value, the maximum value, and even the minimum value, and that depends on the value of this argument in the cos theta, PD sine theta by 2h cross, which can be equal to sum n plus half of pi, where you would get minimum of intensity. These are the minimum, okay, and obviously there would be a maximum where it would be an integral multiple of pi, where n is an integer. So the condition of minima which is stated over here, there is a condition of maxima also, as we had already studied this concept in interference phenomena. This particular concept of this particular condition for minima actually corresponds to the fact that the particle, if we again go into the particle concept of the electron, because the electron, if it behaves like a particle, then either would go through slit A or through slit B and would reach a particular point which was initially not zero. If you close one of the slit, for example, if I close the slit B and then I observe the intensity, then the point which is now zero due to this minimum condition was not initially zero. Now, what exactly is the change in the path of the electron which is caused by the opening of the other slit B? That is what we want to talk about whenever we try to consider both the concept of the particle and the wave simultaneously. The problem is that if one of the slit remains open, for example, if I redraw the picture and I have one of the slit to be open and the other slit is closed, then I have a picture like this. But if I open up this slit, then there is a shift in the pattern of the intensity. So there are certain regions which are not reached by the electrons if both the slits are open, and when you close one of the slit, then these regions the electrons actually can reach. Okay, so that is the dilemma, that is the paradox which we want to resolve over here by using this double slit experiment. Mathematically, this minima condition is arising because we have considered the wave nature of the electrons, and if we consider the particle nature, then it is very difficult to explain why the electrons are unable to reach the regions where you are getting a minima. Experimentally we get a minima, but what is the reason, if the particle nature is to be considered, what is the reason that the electrons are unable to reach over those positions where we get minima? To resolve this paradox, we need to abandon the concept of the fixed trajectory of the particle. It is impossible to have a fixed trajectory. That is the cause, that is the reason that it is impossible to have a fixed trajectory for any particle whatsoever we consider. We have to abandon that particular concept that every particle has a fixed trajectory, because we have learnt, because of the two particular causes. The first cause is that we have learned the uncertainty principle, and the second cause is that in this particular case, the second cause is the presence of this alternate maxima and minima, which can be observed both in the case of double slit experiment as well as in the case of Davison-Germer experiment. So you have to abandon the concept of fixed trajectory. Reason 1, first reason is uncertainty principle. The second reason is either two slit experiment, which I have shown just above here, two slit experiment, or the Davison-Germer experiment, which shows, actually these two experiments both shows the presence of minima, which is only possible if there exists no definite trajectory. So that's how one can prove or that's how one can arrive at the conclusion that it is impossible to have a fixed trajectory. Okay. We have already studied the wave function psi as psi xyz, which can be defined psi xyz t, which can be defined as the wave function or the probability amplitude, and we can also define the corresponding, we had already defined that also, the probability density psi square dx in the case of one-dimensional problems. And in the case of three-dimensional problems, one can define psi square mod of psi square dx for one-dimensional problem and mod of psi square d tau for the three-dimensional problem. This actually, according to the Max Born's interpretation, represent the probability of finding the particle in the region between x and x plus dx, or within a volume between tau and tau plus d tau. So if we talk about one-dimensional problem, then we can say that this actually, let us first of all talk about the one-dimensional. So this is representing the probability of finding the particle in between x and x plus dx. Okay, so what actually is this wave function? If we want to talk about these wave function actually represent the states, and if we want to say that this wave function are to be normalized, then they have a physical meaning. Again, according to the Born's approximation, what is the probability of finding the particle in a one dimension between minus infinity to plus infinity? I can always say that this should be always equal to 1, and this is something which is called as the normalization of the wave function. So this simply means that psi is normalized. Now, even if you have certain mathematical psi which are not normalized, for example, suppose you have a wave function psi prime square dx from minus infinity to plus infinity, which is not 1 but say this is n, then you can always take a new psi to be equal to psi prime by square root of n, such that again you can go back to your previous condition that psi square dx from minus infinity to plus infinity is equal to 1. So one can always reach at this particular condition of normalization of wave function, both from the statistical point of view as well as from the Born's interpretation of probability density function. This is one concept which needs to be kept in mind. There are other concepts which should be introduced in quantum mechanics, and those are all about observables and operators. Now, all the dynamical variables in mechanics can be called as observables. So any dynamical variable, what are dynamical variables? Which actually represents the dynamics which are used to explain the dynamics of a physical system. Those can be momentum, angular momentum, force, position, total energy of the system. So all these dynamical variables can be represented as operators in quantum mechanics. Now, operators can be of different types in quantum mechanics, and these can be actually represented by some alphabets with a cap or a hat over them. Any operator which operates on a particular function can give you a new function which is like a operating on fx is gx, and if I say that my function fx is something like 3x square 4 plus 4 and gx is equal to 9x square plus 12, then obviously we can say that a is an operator which is nothing but a multiplication of 3 multiplied by this, and if gx is this, and if gx is equal to 6x, then we can say that the operator a actually now is defined by a differential operator d dx. So there are different kind of operators in quantum mechanics which would correspond to the dynamical variable. So they have certain properties which are obeyed by these operators. You can always say the properties of operators. What the properties of operators? They can be written as sum and difference. So if one have two operators a plus minus b operating on fx, then they can be written as a operating on fx plus minus b operating on fx. They can be written as a product of two operators a cap b cap operating on fx can be written as a operating on b cap fx. So product of two operators, this product can follow associative law. So a into b into c can be written as a b and then c. Okay, so they follow associative law. They can be a square of an operator can be written as a into a. And there is one important property of the operators which actually is which we will come again later, that is called the commutator. So if we have two operators a and b, and we want to first operate a and then operate b, and then we take another operator b into a, this is called the commutator. This is defined as a comma b. Now this apparently may seem to be equal to 0. So if commutator is 0, then we say a is said to commute with b. If it is not equal to 0, then so if commutator ab is equal to 0, then we say a commutes with b, and not equal to 0, then a does not commutes with b. And if ab plus ba, okay, that there is another operator where you have ab plus ba to be equal to 0, then a is said to a anti-commutes with b, anti-commutes with b. So these are the three. There could be three possible cases for commutator where you have a product of two operators. There are a class of operators which are called linear operator, and they are said to obey only these two properties. An operator is said to be a linear operator if it obeys this two property. What are the two properties? these are A operating on f1x plus f2x, okay, would give us A of f1x plus A of f2x. This is the first property. The second property is if A is operating on a function c multiplied where c is a constant which could be in general of complex nature, then if you can write c of A of fx. If any operator obey these two properties, then that could be, they can be called as linear operator. In quantum mechanics, in physics, all the operators we would be dealing with will be all linear in nature. This linearity is very important in order for the wave function to obey the superposition principle, which we have already seen in double slit experiment. Okay. Then there are orthonormal functions which can be talked about, which we can talk about, and there is another property which would be obeyed by the operators. Those are, that is called the hermiticity or the Hermitian operator.